Hello, my name is Bong Jae Ian. The title of my presentation paper is Improved Structures of Stainless Steel Current Collector Increase Power Generation of Microbial Fuel Cells by Decreasing Cathodic Charge Transfer Impedance. This paper was published in the 2018 Environmental Engineering Research. The order of presentation consists of introductions, materials and methods, results, discussions, conclusions, etc. Introduction. Microbiological fuel cell is an environmental energy system that converts biomass energy of wastewater into electrical energy and purifies wastewater using microbial electrochemical reactions. Although MFC technology has been improving for a long time, many limitations must be overcome to realize it commercially, one of which is the improvement of cathode performance. The power density produced by the MFC depends heavily on the cathodic catalyst activity and cathode internal resistance and is the largest part of the MFC performance determination. There are many types of cathode types, and the most commonly used type is platinum-coated carbon cloth cathode. However, recent studies have developed stainless steel-based cathode coated with activated carbon catalyst, producing more power than platinum-based cathode. Since platinum is known to have better catalytic activity, this result means that the metal cathode base of activated carbon cathode promotes the electron flow from this cathode. SSM is also used as a cathode base to replace carbon cloth by increasing the maximum power density when SSM is added to the anion exchange membrane surface coated with conductive graphite paint. This means that the introduction of a current collector to cathode current can improve the performance of the MFC. The surface area of the current collector affects the electron movement of the cathode, but there are currently few reports of the effect of the cathode collector area on MFC performance. Therefore, the present study hypothesized that increasing the area of the current collector attached to the cathode electrode could increase the electron transfer rate and the amount of power generation. To confirm this, 3 current collectors with different surface areas were tested in a single-chamber cubic MFC with a carbon fiber brush anode and a PT-coated carbon cloth cathode. Materials and methods. 2.1 MFC condition. A platinum-coated carbon cloth cathode was made of carbon cloth, with a PTFE diffusion layer on the air facing, a PT catalyst layer on the solution side, and using the 3 different current collector types. Name is P, PC, PM. P is a broad stainless steel plate, and PC is a broad stainless steel plate with a rounded rim, and PM is a broad stainless steel plate with a stainless steel mesh. And the reactors and electrodes used in the experiment are as follows. 2.2 Inoculation and operation. MFC was inoculated with 28 ml of domestic wastewater and was operated with 1000 ohm. External resistance in a fed batch mode. When the voltage started to exceed 100 mV, the internal solution was replaced. These are solutions that are replaced. And when the voltage decreased to less than 10 mV, the medium was replaced. 2.3 Electrochemical test. The experiment was conducted using a cathode current collector under the same media conditions as the same brush anode, which was a condition to minimize experimental variation. After inserting the AG/AGCL reference electrode into the medium through the rubber gasket, the electrochemical measurement was made by placing it in the middle of the MFC. The polarization test was operated with an external resistance of 1000 ohm for 3 hours after the change of MFC batch, and then placed in open circuit mode for 2 hours before conducting an electrochemical test. Power density was calculated using this equation. Optimum external resistance was calculated using this equation. EIS was carried out in a 3-electrode configuration. After medium change, the MFC was operated at 1000 ohm external resistance for 3 hours. And then, the MFC was connected to a potentiostat, held in an open circuit mode for 5 minutes, and operated at an optimum current in a galvanostatic mode for 20 minutes. The cathode impedance measurement used for each cathode generating maximum power. 2.4 calculation. There are 3 formulas. The first equation is to obtain the Coulomb efficiency. The next equation is to obtain energy efficiency. The last expression is the expression for the potential value. Results: 3.1 power density curves and polarization curves. We can see the figure 2. A is the polarization and power density curves of full cells, and B is polarization curves of anode and cathode electrodes. And Table 1 is analytical data of polarization and power density curves. Electrode potential were written in the SHE scale. The contact area was followed by PM, PC, and P. Figure 2a shows that the performance of the MFC is in the order PM, PC, and P, which suggests that the contact area affects performance. In Figure 2b, we know that activation loss is detected in low current region of in-cathode polarization curves, showing activation loss were originated mainly from the cathode. And see the Table 1, maximum power density, maximum current density, and optimal current density were shown in order of PM, PC, and P. Application of a stainless steel mesh, SSM, to the cathode improved maximum density, optimum current density, maximum current density of the MFC by 8.8%, 3.6%, 6.7%, respectively, comparing with P having no stainless steel mesh. And the optimum external resistance was PM, P, and PC order, but the difference between the resistance values was not significant. An internal resistance, cathodic polarization were shown in order of P, PC, and PM. 3.2 Electrochemical impedance spectroscopy analysis. For more accurate and delicate measurement of ohmic and charge transfer impedance of the cathodes by excluding other irrelevant factors, cathodic EIS was performed in a galvanostatic mode at each optimum current for each MFC condition. Figure 3 is Nyquist plots and the equivalent circuit fittings of the cathodic EIS at the optimum current. R ohm is ohmic impedance, RET is charge transfer impedance, Q is constant phase element. Figure 4 is ohmic impedance and charge transfer impedance in cathodes with different current collectors. A galvanostatic cathode EIS was performed at each optimum current in each cathode. At Fig 3, we know that the P is highest resistance, followed by PC, P. The detailed figure through the Figure 4 show that the highest value was 119 ohm, the PC was 93 ohm, and the P was 73 ohm. Cathodic ohmic impedance of three types were the P was 22, the PC was 21 and the PM was 20, that saw the slightly different values. The three types of cathode ohm impedance showed a slight difference of 22, 21, and 20. However, cathodic charge transfer resistance was significantly different value at the P was 97, the PC was 72 and the P was 53. 3.3 COD removal, Coulombic efficiency, and energy efficiency. Table 2 is CE, EE, COD removal ratio and initial and final CODs for each cathodic condition. When MFC voltage decreased to less than 10 mV, MFC operation was stopped and medium was replaced. These values were calculated using the formula described above. Coulomb efficiency and energy efficiency were the highest in PC, and COD removal was the best done in PM. Discussion. According to the study, carbon cloth produced current collector using stainless plate and stainless steel mesh due to low electrical conductivity, and increased the contact area of carbon cloth cathode using metal current collector, which resulted in decreased cathode resistance and increased power and current density of MFC. The stainless steel plate used at this time has a larger area than the existing titanium wire, allowing electrons in the bianode to be supplied to cathode with less electrical resistance. And stainless steel mesh covers the entire cathode of carbon cloth, so it can directly supply the cathode catalyst. This reduced total cathode resistance in this study. In addition, the three cathode ohmic impedance of P, PC, and PM in this study showed similar values, meaning that the current collector does not significantly affect the contact resistance and material resistance of the cathode. However, a large reduction in charge transfer impedance means that the oxygen reduction response on the surface of the SSM has been enhanced. One of main concerns in the scale-up of MFC is significant decrease of power density as electrode size increases. But, using the SSM may resolve that problem in large area cathodes by facilitating electron transfer and reducing cathodic charge transfer resistance. Another problem is high water pressure. The SSM will help withstand this high pressure as it provides high mechanical strength for the cathode electrode. Activation loss is any voltage loss that occurs at the beginning of an electrochemical reaction. In the present study, cathodic activation loss was the main activation loss in the MFC, showing that abiotic catalyst in cathode is the main source of activation loss rather than the anodic microbial catalyst. Conclusion. 1. Cathodic activation loss was the main activation loss in the MFC. 2. Increasing contacting area of a carbon cloth cathode to a metal current collector increased the power, current density, Coulombic and energy recovery of the MFC by decreasing cathodic resistance. The contact area was PM, PC, and P. 3. Application of a SSM to the cathode improved maximum power density, optimum current density and maximum current density of the MFC by 8.8, 3.6, 6.7%, respectively, comparing with P having no SSM. 4. Cathodic polarization resistance was 47% higher in P, 48% higher in PC, 69% higher in P than anodic polarization resistance. 5. Application of a current collector decreased charge transfer resistance significantly, but affected ohmic resistance negligibly. 6. Significant improvements were observed in the experiment using PM, as this facilitates efficient electronic transmission and effective oxygen reduction reactions on the surface of SSM. Thank you for your attention. Don't forget to click that red subscribe button and give me a thumbs.